Yes, hello everybody. It is an honor for me to give this first talk for Jens. In the year 1960, the first commercial IC appeared. That was the Big Bang of microelectronics, starting Moore's Law. It was from TI. They named it a bistaple multi-vibrator solid circuit. Today we would call it a flip-flop. At the same time, two boys were born in Germany, who would later become engineers. That was Jens and me. Indeed, Jens and I are at the same age as the integrated circuit. Microelectronics has shaped our lives, and along the way we have also had a strong influence on each other. That's why I titled this talk, A History of Influences. Grown up in Germany, we both studied electrical engineering and developed a strong passion in microelectronics. We recognized the crucial role of EDA and became fascinated by physical design. So we both decided to pursue careers in this field, aiming for a doctorate. Jens at the Technical University of Dresden and I at the Technical University of Karlsruhe. We lived on opposite sides of the Iron Curtain. It was the 1980s, but after the fall of the Berlin Wall, Jens joined our institute in Karlsruhe and continued the work he had started in Dresden. So we worked together in the time when Germany reached its reunification. We completed our dissertations. Jens had introduced me to the concepts of genetic algorithms, which found their way into my own research. That were our early years. Then our paths diverged. I joined the automotive electronics division of Bosch. Bosch, the world's largest automotive supplier, where I held various positions. Jens continued his academic career in North America as a postdoctoral fellow and as a visiting assistant professor. This research laid the foundation for his habilitation. After that, Jens also entered the industry, but he first joined an EDA company. At Tenner, he developed place and route tools for standard cells and interfaces. Then he also moved to the user side. He came back to Germany and he joined Bosch Automotive Electronics, just like me. He worked as a tool manager for Bosch's IC design environment, and this happened just as I was taking responsibility for the group, which was, of course, no coincidence. And this period proved to be highly productive. And this is what I want to talk about, automotive electronics. Automotive electronics is a very special world. Let's have a look on it. Modern cars contain about 100 control units. Many of these systems are safety critical, meaning that human lives depend on them. Just take a look here on these examples. It does not work very well. For this reason, the big challenge in automotive electronics is reliability. And there is a second major challenge, it's analog design. These challenges grew even more significant around the turn of the century. And the driver we see here. By the late 90s, the BCD processes used in automotive chips had also reached the submicron range. That was just the time when Jens joined Bosch. Smaller structures made the circuits much more sensitive, giving rise to new problems such as electromigration. We heard of it, a major problem for reliability. And it pushed also integration of more and more analog circuitry, so the analog IC content started to grow rapidly. Let's first consider the reliability constraints. Automotive electronics have to run in very harsh environment, look at the numbers, for many years and completely free of failures. A comparison to consumer electronics shows that automotive electronics is really a completely different world. One big problem that arose was electromigration. Now, what is EM? This has already very nicely explained Sakin. This is the thing with the electron wind and the dependence and Black's equation. Sakin had explained that in his talk, so I want to go over that and show you typical failures. Typical failures are where the material migrates away, voids occur. These can lead to breaks. This is a picture from Bosch. Where the material accumulates, it grows into the insulating layers known as hillocks or whiskers and can lead to shorts between neighboring wires. And from the point of an automotive engineer, the behavior of him is quite nasty. This is an aspect I want to emphasize because it is a long-term effect. You cannot identify vulnerable wires by an end-of-line test. And to make things even worse, it can have a positive feedback loop. That means if it happens, you will see it in the field. And of course, this is a nightmare for automotive. Why positive feedback? Now, look at this void on the right side. This wire still conducts the current, but at the expense of an increased current density. And this means exactly here at the weakest point, EM will probably accelerate until the wire is broken. And that means we must make sure that our layouts are EM robust. But at that time, in 2000, there was no tool for that. Tool providers have proposed to work with net properties. Yeah. But of course, this doesn't work because you have to consider each net segment separately. Sakin has explained that. So we decided to develop our own tool 25 years ago, and the result was MSIM. MSIM is capable of calculating the current density in metal structures. This example shows a wire in which the current density exceeds a defined limit, and the layout has been improved as shown on the right. And another example, here we see a layout with a VR array. MSIM shows that the inner VR receives too much current due to uneven current load, and in this layout the layer change and the change in current direction from X to Y are decoupled, and this distributes the current evenly across the wires. So MSIM became the mandatory check tool for all automotive chips at Bosch. And by the way, it was developed by Göran Jelke, who just has given a presentation this afternoon. In 2004, he received the EDA Achievement Award for this work. And also, by the way, it was Jens who brought Göran into our team at Bosch, and he is still at Bosch. How long, Göran? Approximately 30 years now, I guess. Some may wonder why Bosch tackled the EM problem so early, even though Siemens was already 5 generations ahead. And the answer is here. Currents of more than 10 amps can flow in an automotive chip. Can you imagine that? At the same time, there are also very small currents. Currents and voltages span many orders of magnitudes, and that's because automotive ICs integrate entire systems. They are SoCs, and that brings us to the second challenge. So let's talk about analog design. Electronic systems, as cars and also others, have to interact with the real world, which is of course analog. They need to convert sensor signals at their inputs and to drive actuators at their outputs. These parts are all analog. And all these parts, including digital, need power supplies, which are also analog. Here is a typical automotive SoC. It has logic and all the analog stuff I talked about. Now, the analog area comprises only a few % of all components. However, the design of these analog parts requires far more effort than the digital parts. Benjamin has explained that in the last talk. So it seems that analog design is a much more difficult task than digital design, and the question is, why is that? The short answer is, analog circuits are much more sensitive to disturbances. And there are many disturbances. They come from fabrication tolerances, temperature effects, mechanical stress, many kinds of parasitic effects, including these substrate problematic. Klaus Heinrich has explained also this afternoon. Of course, all modules, and there are disturbances coming from outside. Of course, all modules, the analog and digital ones, are exposed to these influences, but digital signals are far more robust against them. And the reason is because they are value and time discrete. Disturbances make it look quite different than this ideal signal as we normally look at it. In reality, it may look like this. But this is no problem in digital. This can be handled by defining a forbidden voltage region and restricting read operations to times where no signal transitions happen, then everything works correctly. So dealing with disturbances thus becomes a matter of timing. Or in other words, timing is the key to managing the quantitative complexity. With analog signals, such a simplification is not possible. Each effect has direct impact on the signal quality and must therefore be considered individually. This is a problem of qualitative complexity. How do analog circuits deal with these disturbances? How can they be managed? They are controlled by special design techniques that utilize the symmetric component behavior. And this has to be supported by the well-known matching techniques in the layout. You have heard about it, I'm sure. Parasitic effects require additional special layout methods, and these techniques together is what we call the art of analog layout. And the key point is here, why I'm talking about that. All of these requirements are constraints and can, or better said, they should be handled as such in the design process. Now, what was the situation around 2000 in terms of constraints? How were they handled in reality? Well, by notes and schematics, tables and discussions, and that was, of course, too time-consuming and unreliable. To overcome these problems, we wanted that constraints become part of the design data, so we began to develop a concept for constraint-driven design flow. Teamed up with leading semiconductor companies and tool vendors, publicly funded projects, and from this collaboration emerged the constraint management concept, which is part of today's design tools. Here is an example of defining placement constraints, supporting various constraint types, such as spacing and orientation and so on. Another example, here we see the cross-probing of symmetry constraints, along with an interactive feature that helps implement them in the layout. The matching function arranges a matching group according to a user-defined pattern, including dummy elements, also possible here. These works on EM and constraint-driven design influenced EDA worldwide. After this highly productive period, our paths diverged, and in 2002, Jens returned to academia as a professor and director of a renowned institute at the University of Dresden, as we know. I myself moved within Bosch, taking responsibility for the layout of all Bosch chips. And in these leadership roles, we had the freedom to continue working together in different ways. I would like to highlight some of the resulting mutual influences. Jens pushed forward the research he has started at Bosch during all his career. Let's start with constraint-driven design. It turned out that the utilities in the tools were useful, but they targeted only parts of the flow and were not really end-to-end. So until about 2011, the focus was on theoretical groundwork for a new seamless design flow. Over the following decade, many contributions were made to put constraint-driven design into practice. And this work is closely associated with one name of a man who is here also today, Andreas Grinke. He tackled existing problems at the root, developed new concepts for constraint management, and put them into practice. Andreas developed a generic approach that allows constraint to be propagated throughout the entire design process. His method also allowed a flexible handling of constraint during the design process. That was exactly the kind of flexibility that industrial practice requires. Even more extensive are Jens' contributions to electromigration. In the first years after leaving Bosch, Jens continued to push this topic forward together with Göran. Very early on, he had foreseen that EM could become also a problem even in digital circuits. And in fact, he first mentioned that in 2005, long before it became a real problem there. In these works from 2012 and 2013, he already addressed this issue directly. And by now, migration problems, we know, have long since reached modern digital design, and Jens has contributed many invaluable insights into understanding and managing migration effects. I would like to highlight one recent work with Susanne Rothe. She's also here as first author. The work demonstrates how migration effects can be incorporated into an industrial flow. Sakin has also explained that. I would just like to add one hint. As I understood, the method is also able for estimating the material parameters that are necessary from standard lifetime testing. And that's not all. He published also a textbook. We also have already seen that in Sakin's talk. So Jens also supported education, and I can honestly say that I have learned many things from this book, such as mutual interaction of electrostress and thermal migration and other effects that I had never heard before. Yeah? Such as the bamboo effect. We also have heard it, where grain boundaries act as barriers, or the, for me, surprising fact that it makes indeed a difference where the current flows through a via from bottom to top, or vice versa. Did you know that? I did not know that before the book came out. I think it's a must-read for anyone in the field. Now, once more, this slide, it's the last time. In 2010, I received an offer for a professorship in EDA at Reutlingen University. I accepted. And I think it was also Jens' example as a successful EDA professor that played a decisive role in my decision to accept. So just as he has followed me into the automotive world 10 years ago, I now followed him into the academic world. And Jens has been a valued mentor ever since, inspiring several important joint contributions, and two of which I will highlight at the end of my talk. 20 minutes, I see it's. As a committee member of ISPD, Jens aimed to establish analog layout as an additional topic, and today we see how successful he was. With this goal in mind, he encouraged me to co-author a foundational paper on the subject and invited me to give a talk. In this way, I attended ISPD for the first time, and in the paper we investigated the reasons why automating analog has failed so far. We derived two visions that we called a continuous design flow for interactive layout and a bottom-up meets top-down design flow for analog layout automation. I think that is exactly that was Benjamin was talking about today. It has attracted significant attention within the community and has shaped especially my work to this day. And it was Jens who encouraged me to co-author the paper. Without his support, I would have never written. And the last thing is, he asked me if we wanted to write a new textbook on layout design with him. So up until then, I had known only these textbooks on layout design, including the excellent work by Alan Hastings, from which I have learned a great deal. But all of these books have their purpose, but are worth reading, but they are all over 20 years old, and so Jens' idea was therefore to present the topic comprehensively for the first time in a new book, and that convinced me. So our reference book was published in 2020. It covers really all the fundamentals of layout design and highlights every aspect an engineer needs to know. It is also available in German. It was a tremendous work, but today I am pleased that we wrote it with more than 40,000 accesses to date. It seems the book has really filled a gap. Also, this work would not exist without Jens' initiative and, yes, his persistence. Dear Jens, thank you for all your valuable contributions and especially for the support of the community and also for the support of my career. Thanks, and thanks for your friendship.